Welcome to my world. It is another period, another season, another time to really dish out my usual. Knowledge is power, health is wealth. We acquire more knowledge, the more we try to unravel the mysteries of the world. There are so many mysteries, and as a medical laboratory scientists, our efforts are geared towards making all mysteries non-existent, explainable. So when you unravel the mystery in certain things, then the matter becomes easy to treat, and the outcome becomes very, very predictable. Today's topic happens to be unraveling this envelope viruses and code. Unraveling envelope viruses and code. The period that you are right now may be not the code season, but what I have found out, and many people have found out, is during the code season there are envelope viruses really devastating. We can remember the influenza virus devastation of 1914 and even 2020 COVID-19. They are not things that one can say are joyful occasions. They affected both the economy, the well-being, and other things that are very important to human. But the things that we have learned is what will help us to prevent a future occurrence. So these observations would open all the secrets that is behind this continuation of having the experience of envelope or other viruses really devastating mankind. The effort today is to really study what is the arsenal of envelope viruses, especially, that makes them very, very devastating when they attack during the cold season. So let us sit and watch, or continue with the slide section.
We start here. Unraveling envelope viruses and code. This is very important for us to understand the secret of these viruses. Virus components. When you are talking of envelope viruses, you are now talking of every virus are made from the nucleic acid. Without the nucleic acid, there are no viruses. So the nucleic acid are basic and essential to all known form of life. They are composed of nucleotides, which are monomers made of three components: a 5-carbon sugar, a phosphate group, and a nitrogenous group. If the sugar is a compound ribose, the polymer is called RNA, and if it is deoxyribose, the polymer is deoxyribonucleic acid, DNA. Now look at nucleic acid that I've just explained. You can see the aggregate is what is called the nucleic acid. The single ones are called nucleotides. Now the single capsomere, that is the protein that covers it, it has a single unit called capsomere. When they aggregate together to form a shape, they are now called capsid. So this aggregation covers the nucleic acid and form the icosahedral symmetry, that is arranged in equilateral triangle. The symmetry is there. Then it could be helical, that is in a kind of helix form. This is equilateral. You can see the nucleic acid inside, and all that is covering it, protecting it, is the capsid. The capsid, when it's like this, is called the naked virus. But when it's now covered with the envelope of the plasma membrane of the whole cells, it is now called envelope virus. So you can see there are spikes, especially like the COVID-19 virus, virus, COV2. So it's very important for us to understand these aspects. Yeah. We now have the fact to be appreciated in this matter. First of all, the upper respiratory tract infection increase in frequency, especially in autumn and spring, and remain raised through winter. So the envelope viruses are more or less concentrated with matters of upper respiratory tract infection. That's where you get majority of these envelope viruses. This envelope comes from the infected cell or host in a process called budding of when they want to come out of the cell. During the budding process, newly formed virus particles become enveloped or wrapped in an outer coat that is made from a small piece of the cell plasma membrane. Envelope viruses are sensitive to extreme pH. That's a fact, especially that is present in the gastrointestinal tract. So you can imagine something that is so sensitive. How can it cause slower intestinal problem? Once you are going to the small intestinal and probably you may not even find any of them there because they must have been more or less destroyed by the extreme pH. Heat, dryness, and simple disinfectant affect them. Also, their surface glycoprotein requires petrolatum to really activate. The envelope viruses pose an important health threat because most of the persistent and many emerging viruses are enveloped. Advantages of the envelope is envelopment allows the virus to exist from its whole cells using the cellular machinery for exocytosis, thus avoiding cell damage and preventing immune response. Once there is a cell damage, the inflammatory response will happen immediately too. So it wants to go like a thief without being noticed. That's why the advantage of being enveloped. The envelope increases the packaging capacity of the virus particle and allows for carrying additional viral protein, which the body may not be able to react against itself. Envelope protein on the surface of the virus have a higher structural flexibility than capsid protein because they are not part of a rigid capsid structure. Thus, envelope viruses can escape neutralizing immune response better than their non-envelope virus, just like I earlier said. Most zoonotic viruses are enveloped. Apparently, variation of envelope protein facilitates adaptation to different hosts. These are the family of these envelope viruses, so listed: the Herpes viridae, the Pox viridae, the Hepatitis viridae, the Retroviridae, virusoid, and so on and so forth. So, example of the herpes, you have the herpes simplex, which is even accumulated in other problems that are associated with even this Down syndrome. Varicella zoster, EP virus cytomega, the virus. When you now talk of pox virus, the most important has always been smallpox, but now the attenuated Yersinia virus, and so on and so forth. So when you look at this list, you can get the their real name. So it's very important. They go on also to coronavirus. This Filoviridae is the family name for Ebola virus and Marburg. You know, all these family are not that every member of the family really cause, are enveloped. So the ones that are enveloped are listed on this side. So if it's envelope, you get the name again. Successful vaccine against several envelope viruses have been established. On the other hand, newly emerging viruses cannot be targeted by vaccines, and there are no vaccines approved yet to prevent infection with several important human pathogens such as hepatitis C virus, HIV, cytomegalovirus or EP virus, EB virus. Furthermore, despite an effective vaccine against hepatitis B virus and others, chronically infected and need curative therapy. How they propagate themselves. We identify the seasonality of rhinovirus because if you look at the time they really come out, what really makes them come out, then you can understand how they propagate themselves. The adenovirus is a naked virus, it's not enveloped. The influenza A and D viruses are enveloped. Human parainfluenza, RSV, human metapneumovirus. Not all are enveloped and all are located in respiratory samples. So you can get them in the respiratory samples, and that is where they really propagate themselves. We know very well that when a patient or anybody is immunocompromised, that is, the defense mechanism is lower than havoc by these opportunistic viruses could happen. Majority of them are pathogen regardless of whether their defenses is perfect or not. So once they are there and they cause problem. But some are there, they are not causing problem until when the opportunity for really creating that problem arises. Non-envelope viruses are present throughout the year, so you expect them, but there is also this aspect that majority of them that are listed, adenovirus, influenza A, B, RSV, prefer low temperature. RSV and influenza A virus prefer a narrow humidity too. So you are talking of how they propagate themselves. These are conditions that they prefer to really prosper. All these translate to explain the increase in activity of this at certain period of the year. Viral seasonality explained. The effect of climatic condition on host resistance to infection is very important when you want to really explain why the seasonality, which is the purpose of this exposition, the video. That is, during this cold season, you experience low vitamin D level following lack of sun, especially in the winter areas, the areas where they have winters. So sun exposure can affect our ability to fight infection. We know sun is very necessary for vitamin D. Then the 2 is the effect of behavioral change on transmission. Around this period, people are more indoors because of the cold season, and holidays are around that period. Although the summer holidays are 20, but you find people more indoors during this winter season because you can hardly move around. So spending more time indoors in close proximity to others, and even children are all together. These are people who are probably can be regarded as immunocompromised, so the infection can really prosper. The diminished immune response in a chilled environment. It's a general phenomenon. The reactivation of dormant viruses by chilling for the increase in upper respiratory tract infection during the colder months. So the dormant viruses, they now express themselves. They come out. They are like they have enclosed themselves, like they are in the cyst, cover themselves with things that will protect them from the harshness of the environment. But the moment the environment, that chill environment comes into existence, they now reactivate themselves. Integrity of influenza A virus envelope are better at lower temperature, while in warm temperature the envelopes leak, and the virus is susceptible to damage. An association of absolute immunity with hospitalization due to influenza, lower respiratory tract infection, and not with a lower respiratory tract infection due to rhinoviruses or respiratory syncytial virus. So these could explain the seasonality very well. There are other parts which are not included. The treatment you can think of, when you are looking at the envelope itself, the only one that attacks the envelope is this one, the drug oseltamivir and the tecovirimat. This is what the smallpox as well, and this is what the virus. So you can understand that not much of these anti-envelopes treatments or drugs are available. So it shows to a certain degree that the concentrating on the envelope attack may not be very successful, because the majority of this envelope is like attacking the plasma membrane of the host itself, because the envelopes are more or less the plasma membrane. You have this as well. And then the vaccines, these are all names for smallpox vaccine, hepatitis B virus, measles virus, we have mumps virus, influenza, rubella, and all these are vaccines. Then the drugs against, we have drugs against HIV, hepatitis B, hepatitis C, hepatitis HIV, lamivudine. These are all names of drugs that you come across. Some of these drugs have no name yet because they are undergoing clinical trials. When they are successful, you now find them very useful to give them names, because they are now to be marketed with their brand name. Thank you for listening.